So now we will continue. I mean, what is the best practice for working with neural network, which is a convolutional neural network? So the receptive field dimension, we need to define it. So the default is 2D for images, but it could be 1D also. So we can work with words, for example, in a sentence, or 3D for videos that adds a time dimension. The receptive field size, the batch should be small as possible, but large enough to see features in the input data. So it's common to use 3 times 3 on small images and 5 times 5 and 7 times 7 or more in larger images. So for AlexNet, for example, they use 11 times 11. Stride widths, use the default stride of 1. It's easy to understand, and you don't need padding to handle the receptive field. Falling off the edges of your images, this could be increased to 2, for example, or larger for larger images. Number of filters also. So filters are the feature detectors. Generally, fewer filters are used at the input layer, and increasingly more filters used at deeper layers. Padding, we need to set to 0 and call the 0 padding when reading non-input data. This is useful when you cannot or don't want to standardize input image size, or when you want to use receptive field and the stride sizes that don't neatly divide up the input image size. So those skills will come with time. So max pooling, for example, or pooling is a destructive or generalization process to reduce overfitting. The receptive field size is almost always set to 2 times 2 with a stride of 2. Usually, to discard 75% of the activations from the output of the previous layer. So it's 2 times 2 with a stride equal 2. So we keep quarter of knowledge, in fact. Data preparation, consider standardization input data, both as a dimension of the image and the pixel values. It's common also to pattern the layers in your network architecture. This might be 1, 2, or some numbers of convolutional layers followed by a pooling layer. This structure can be repeated 1 or more times. So you can just have number of convolutional layers followed by pooling layer, and you need to repeat this structure maybe several times in your model. Finally, fully connected layers are often only used at the output end and maybe stacked 1 or 2 or more deep. Dropout, CNN have a habit of overfitting, even with pooling layers. Dropout should be used such as between fully connected layers and perhaps after pooling layers. So this dropout is important because usually convolutional layers overfit. We have here some examples. We need to start practicing some convolutional layers. So I will just talk about CIFAR10. It's a data set. There are 2 versions, the CIFAR10 and the CIFAR100. CIFAR10 data set, it consists of 60,000 images, and each image is 32 times 32 pixel values. And it's a color image, which means we have RGB. So in fact, the image or the volume size should be 32 times the speed. We have 10 classes with 6,000 images per each class. We have 6,000 images per each class. Those classes are, for example, airplane, cars, bird, cat, deer, dog, frog, horse, sheep, truck. So there are 50,000 training images and 10,000 test images. So it's very similar to MNIST dataset. But MNIST dataset, it's a grayscale, and we have 10 classes also. So it's almost the same. The dataset is divided into 5 training batches and 1 test batch, each with 10,000 images. The test batch contains exactly 1,000 randomly selected images from each class. So all classes are equally represented in the training dataset and in the test dataset. The training batches contain the remaining images in random order. So if you want to download CIFAR10, you can get it from keras.datasets.cifar10 import I mean this load data, right? So you can just make it as you want. So you can download it from this website, or you can just get it directly from Keras.datasets. It's a very, very nice one. So maybe your first CNN model, you can just play with CIFAR10, for example. CIFAR100, it's the same, but this one has 100 classes. This one has 100 classes, each containing 600 images in each class. So there are 500 training images and 100 testing image per each class. So in fact, this one it's the same, but we have 100 classes. For each class, we have 600 images, 500 for training, 100 for testing. The 100 classes in the CIFAR10 are grouped into 20 super classes. So we have those super classes and those under classes or super classes. For example, fish, we have aquarium fish, flatfish, ray, shark, trout. So we have those super classes, we have those under classes, for example. So you can get it from Keras.datasets and import CIFAR100. And also it's, I guess it's, I don't know, is it 32 times 32 or 64? CIFAR10, 100. I don't know the image size. What is the image size of CIFAR10? So whatever, I mean, yeah, so another image, another data set, it's a color facial recognition technology data set.
It's the same. It's 32 by 32.
32 times 32, yes. For this data set, it's 8.5 gigabytes of faces for training facial recognition. So it consists of 14,000 images to around 1,200 persons with 365 duplicate sets of images that were taken on a different day. You can download it. I don't know if you can get this one from Keras. Can you check if you can download this one from Keras? Because it will make life much easier. And can you check, do we recognize people, try to recognize people or mode or, because it's a facial expression. It's facial recognition software, yeah. Is it faces, persons, or different mode, for example, happy, sad, and stuff like this? And also, can you check maybe the size of each image? What is the size? I guess it's like, because it's have all maybe facial expressions and happy, sad, neutral, something. We can do it. Can you check? Did you check it?
No, for Keras, I was checking. There is nothing.
It's not in Keras,
but there is something in GitHub.
Okay.
Which can be cloned.
Yes.
The size is 384 multiplied by 256.
Okay. And the output, what is the labels? So can you start building your model for CIFAR10? Can also online, can you please go to Colab, for example, and start building? You have this, you can download it from Keras.datasets, import CIFAR10. You will use this line for getting a train test containers or data, for example. Just load data, you will get your data set. Can you try to build your model? Can you go to Colab and build a model for this one, deep learning? So online as well, can you please go for Colab and start build a model for for CFAR10, we have 10 outputs. We have those images. We have 10 classes. So, white train, in fact, it will be number between 0 and 9 because we have 10 classes. So you need to use 2 categorical to convert it into 1 hot encoding. Did you run your code, Simon?
Mhm.
Is it working with you?
Yeah,
Do you want to share your screen?
no. My computer is struggling already.
Okay.
Yeah.
Anyone online who has his code running, so we can share his screen with us? Hello guys online. Anyone has his code running? I need to check if I have CFART and yes. We have a sample CNN model and we can achieve accuracy of, I don't know, what is this number? So if you want to get help, you can get help from the next slide. I just use the very simple CNN, sequential ABI.
In that collab, it overfits, right?
It overfits.
Yeah.
Yes, you can see it here, right? Training, I mean, validation accuracy, it goes down now, maybe after epoch number 9, right? Maybe you need to make more, maybe, because this model is very simple one. Calculate number of parameters. I used here SGD, maybe you need to use another optimizer. Maybe another optimizer you can get better results. We are discussing, so please online you can just unmute your mic and did you make your code, Fiona?
Yeah, or I found yours on your page.
Did you make some changes to improve performance?
Trying to run it, and then I will change.
Yeah. So can we calculate number of parameters here for this model, for example? Can we get this number 96986? Yeah. So can we calculate this number here? So this number, in fact, we selected here in the input layer, we selected the kernel size is 3 times 3, but the input image, it's 3 channels, right? So it's 32 times 32 times 3. So number of parameters will be 3 times 3 times 3 times the number of features, which is 32 plus 32. It will be this number, right? And
32 multiply 3 multiply 3 multiply 30
multiply 3
3
plus
plus 30.
32. Mhm. So we will use here dropout with this dropout rate 4.2.
20%.
Yes. And after that, we will use another layer. What will be the number of parameters here? What will be the number of parameters here?
Like
3 times 3, because this is a filter size,
Yes. Multiply
times number of features here 32,
plus 32.
times 32 again, plus 32,
Yes.
right? So again, it will be 3 times 3, because this is the depth, number of channels,
Yeah.
depth. So it will be width, length times depth. So it will be 3 times 3 times 32 times 32 plus 32.
Yeah.
We will use max pooling. What will be the output from this max? What will be the size of this max pooling? When we use max pooling, what will be the size? When we use max pooling, do you see? We use the 2 times 2 max pooling. So the size, the shape has reduced to half from 32 times 32 into 16 times 16 because we use the max pooling. So now the feature map has been downsampled into, we have 32 feature maps. The size was 32 times 32, now it's 16 times 16, right? So now we need to flatten. So anyway, I mean, we flatten because this is number of parameters. We will flatten it, and we will select the first dense layer of 512. 512. So number of parameters here, how will be the number, how many parameters? It will be 512 times this number plus 512. So it will be this huge number. And imagine if we didn't use here max pooling, this number would be much, much larger. No, it will not be, it will be the same. Right? It will be the same, sorry. I mean, it's better to use maybe max pooling here between 2 layers. Because now it makes no sense in fact. Right? Mhm. So we will flatten max pooling. Sorry, you are correct. I mean, it makes sense because this max pooling, those features will be the input to the next layer. I'm sorry. So it will be 16 times 16 times 32. So when we flatten it, it will be the size, right? 16 times 16 times 32. Can you multiply? Mm-hmm. We flatten the feature map. So it will be 16 times 16 times 32. So it will be 8192. 8192 when we flatten it. But there is no parameters. But this is when we flatten it. This number, it will be this number multiplied by this number plus this number. So it will be 8192 times 512 plus 512. So it will be 419, 4816. So now we have those. After that, the output layer, we will use dropout. Dropout does not have any parameters, right? It has, and after that, the output layer, the output dense layer, it will have 10 outputs, right? So how many parameters here? It will be 10 times this one plus 10. 10 times 512, so it will be 5,120 plus 10, it will be 5,130. So this is the number of parameters and the size. Yes. So please online, do you have any questions? Any questions online? Should we stop here today or should we?
I think it's.
Okay, because the next example will be CFAR10, but you can do it at home. Try to change this structure because this accuracy is extremely bad, right? We need really to find good structure to solve this problem to get maybe 95, 96, 98% accuracy. We need to reach this level. You can also try here to use transfer learning. You can try to use VGG16, for example, which is very easy for feature extraction. So you can, so this one, it could be like a small home assignment for next week. We can just get someone to present his solution next week for this problem. He will be using, he will just improve this one. We need to get maybe 90%, 95%. You need to fix this structure because this one is not good, right? And also, maybe he can try to use a transfer learning. VGG16, for example. I mean, VGG16, the input size should be 224 times 224. So you can downsample, right? Or you, so how you solve it? And try to use VGG16 with this example. Yes. Okay. So we will stop here, and we will continue. We will meet again next week. So next week, some people will present their project, and also, please, I mean, someone can just take this problem like small home assignment and can present it next week. So in this problem, we need someone to just develop his algorithm, his structure from scratch, and we need someone else also to try to use transfer learning. Yes, thank you very much for today, and we will meet again next week.
Thank you.
Thank you very much.
Thank you.
Thank you very much.